is the product size, distribution, and the power. So there's the 2x2 that you saw previously here.
Yeah, that's one thing that is probably recommendable to highlight is that, as you can see there in the design simulation, you already have the PID loops on the process. So there is a valve, for example, in the feed rate, there is a valve that is actually commanded by a PID loop. And in the case of the motor, there is a PID controlling the speed. So that's the normal configuration around an APC controller. The APC solution sits on the top of the normal regulatory control that you have on the plant, the normal PID loops. So effectively, the APC software is changing the set points remotely of those controllers. So instead of the operator changing set points, is an automated system, computed system, that is changing the set point for the operator in an optimal way. Yeah, that's why normally we say that the APC software can be compared to a cruise control mode, because the operator sets wherever the limits are for the variable, he switches on the APC, and then the APC takes care of the set point and how to optimize the system within that envelope.
So here you can see that here is the set point of the flow controller, here is the set point of the speed, and as Christian was saying, so what you see here in between here is the current value of the two, and for APC, instead of setting an actual set point, you set the high and low ranges. So this is the low range, these ones here are the low range, and these are the high ranges. And basically you're saying, you're telling the APC, you choose where should I be in between here. And these ranges, these low and high ranges are set by here. So here the operator can enter the low range. So you can see now the low range has increased. So what the operator does is not put a set point, but put these ranges for both the manipulator variables and the control variables. So here I'm saying, for example, for my power, that my upper limit is 470 megawatts. So the controller will not let the ball mill power exceed that limit there, because I've defined that through this limit here.
Can I ask questions?
Yes.
Can you show the model that maintain prediction within the APC and how it was defined, this predictive model? This is first question. And the second one, can you show the PID parameters inside the DynSim and make a kind of comparison of these parameters with APC, what was defined by APC, the predictive model?
Right. Okay. So I'll answer the second question first. With this example, there is no. Remember that there is no controller loop between these two variables and the power. So there is no PID loop between this and this, or this and this. In this example, it's open loop, so the operator is doing this. So in some case, in this example, we're potentially replacing the operator. I could try and find out other examples where we actually remove the current PID and replace it with the APC. We can do that. If that is something that you want to use as a demo, it's something that we can look into for comparing. But for this particular example, we're not replacing a PID with the APC.
Yeah, this I understood. I mean, I just want to see how the PID of real control loop are loaded into this model, in DiceSim model.
Okay. Okay, so here you double click. Okay, I need to turn the simulation off. Wait, no, maybe not. So here in the tuning, here's where you enter the parameters of the PID. Is that what you're asking?
Yep.
Okay, so that's how you would enter it. So I did miss some details here. So each one of these items that you see here, you have to configure it. So what you'll have to do is enter certain parameters about the component. So every time you go to the template here and you drop an item, what you'll need to do is actually do the configuration, which is filling out all these information. Some of it is basic about, say, for example, the physical shape, how big the mill is, for example, or an example here, the diameter of the grinding media. So all these parameters you need to tune so that it represents your model, represents your plant. So when we look at the DiceSim, there are three main components. One is actually building the flow sheet that you see there. The second bit is then the configuration bit, the initial configuration, which is entering these parameters. And then the third bit, which is the most time-consuming bit, is the tuning, is the trying to identify the exact values of these so that it is a good representation of your plant.
Yeah. Also, you have processing parameters, like all the parameters that are described in the equipment. And also you have process control parameters, which are the parameters describing what is the control strategy behind the PFD or the diagram that you are trying to represent. APC, normally, I believe 100% of the time, the APC don't really mess or they don't really change the PID tuning of the control loop. The APC only changes the set point, and instead of the operator changes the set point, the APC software only changes the set point. But the underlying tuning is exactly the same, so it's using exactly the same P, I, and D parameters that the operator could have been using.
Yes.
So that's really important. That's really important because one of the key things that you do on site survey is to assess what is the current status of your normal regulatory control. If there are oscillations around the process, or if there are not really good regulatory process control in terms of PID control. If the current status of the plant is not in good condition,
that's
the result of implementing an APC is not really powerful.
You were saying?
Sorry, I absolutely agree with you, Christian. I just want to add that probably tomorrow there might be a lot of questions of how APC will define a predictive function. In this case, as I understand, as you described, we put APC control tuning parameters manually into the APC environment, but in the real life we need to do a step testing, right?
Yes. Okay, so I'll run through that process now. So you can see here on the left-hand side, you see the main stages of developing the controller, the APC. So the first step here is the connection. How you're connecting the APC. So in this instance, I'm connecting via an OPC connection to the DiceSim. So in the real plant, it would be either a DCS or your PLC system. So that's the first thing you'll need to do in the configuration. The second step is, as you were saying, is the step testing. So APC comes with the auto generation tool. So what you do here is set for each control variable, for each NV here. What you do is you set how the step test is going to generate. So here you say the length of the step test, what is the average value, so this is slow rate, and you can change, and we set the high and low limits where the step test can only work between.
Right.
It's a key functionality of the APC software because it allows you to do the step test in an automated way.
Yes, in a controlled manner.
Yes. So you just have to specify the limits and the amplitude of your manipulated variable, and it will create a PRDS, which is basically
a random step. And the thing that it does here is that it moves all the NVs at the same time. All the NVs at the same time by these definitions. And what the tool does is that it makes sure that while it's doing the step test, that it doesn't violate these limits.
Yeah, now this is a functionality that is optional. It's always there in the software, but normally in the plant, if you are telling the operator that you're going to move 2 or 3 manipulated variables at the same time, they get a little bit upset. So if you want to run your step test manually and do the step test in an old-fashioned way, you can always do that as well. But the software comes with that extra functionality if you want to use it.
Yeah, so there's 2 ways. One, you can do it through this way, or the other way is you can do it manually, and then you can import the data for the identification process.
Mm-hmm.
So once you've generated the step tests, either manually or automatically through this process here, you then have a data processing section here. So here are all my tags, and what you can do here is some signal processing, some cleanup of the data, or some manipulation of the data. You can take the square root, the log of the data, or add variables together. So this section here is about data processing. It also has some data mining options for you as well to generate some statistics. So this area here is about processing the data. Once you have that, then we go into the modeling side, which we're asking here. So here in the modeling side, once I have generated the step test, once I've generated the data, once I've cleaned up the data, I then here select what are my manipulated variables, what are my feed-forward variables, and what are my control variables. And then what I do is then I run through here a sequence of identification processes. So normally this is sort of the default prediction. It has a recursive, partial. I won't get into any of these details, but basically what this process here is using the data that you've generated, it identifies models.
Yes, there are 2 main, probably we can discuss this tomorrow with the guys there, but there's 2 main type of identification techniques. One is the finite input response, FIR, and the other one is IRX. Normally, in the first order type of responses in the process, most of the time you use FIR. Each technique is really well documented and mathematically explained, and most of the software from our competitors are doing exactly the same identification techniques.
What we can do after this presentation is I can send you the manual of the APC, so you can have a look in more detail there of how to do this. But in essence, this is the software. We'll have an algorithm internally to generate the models for you. All you need to do here is do the pairing. Is set this configuration up. And once you've done that, then you have can see this is my manipulator variables, here's my feed, here's the speed, and this is the shape of the curve for the particle size distribution and for the power. So you can see here, if I do an increase here, I'll get an increase here in power. Does this answer your question?
Yes, it is showing actually the matrix of controller, the connection between parameter, how the manipulated variable affects to control variable.
Exactly.
This what Julio is showing at the moment is the result, or could be the result of multiple identification processes. So the final model are actually selected from different sections or different tests that you can run. Once you are happy with the result, you select the best set of models that you got from different tests, and then you compile a final linear model. The final linear model is the one that will be used in the final solution.
Yes. So I am skipping a lot of steps here, but just to give you a feel of how to go from the start to finish. So yes, here's where you do the initial structure. Here's where you do the software will do the identification, and this is the final output that you get from the controller.
One thing that is valid to highlight, as you can see, the software is very, very detailed. So the software is not really intended to be used for operators.
Yeah.
The software is an engineering tool for the control engineers that will develop the application. So the normal interaction of the operators with APC is through dedicated HMIs that have to be created in their DTS or in their SCADA system.
Yep. So now, what I've showed you so far is just the model. Now we go into the controller tuning. So similar to the PID, this is the controller tuning section of the controller. So here is where all these variables, like NV priority, here's where you set the limits, the initial limits. There is also some control variables, some other variables here. All these variables here need to be configured, like priority, cushion. I won't go into any of these details. There is more information in the manual, but all these are the tuning parameters for the APC. And you can think of these like the PID of the PID parameters for the PID controller.
Yeah, so effectively, this is where you make certain variables to react faster or slower or more aggressive or less aggressive. This is effectively, you have a lot of parameters there to play. You also have priorities in terms of economical factors, priorities in terms of moves. You can give weight to different moves. We can be talking about that for hours. Yeah, so in summary, there's a lot of parameters that allow you to make and achieve the process response and to make the client very comfortable with the final solution. Yeah.
Mm-hmm.
Yeah, so here you can see there's more parameters. So for each NV, there is an NV weight and a target weight. So these, as Christian said, these are the parameters you need to tune to speed up or slow down the controller, like the PID controller.
Now, from the operational point of view, the most important things to understand is that for control variables, PDs, or manipulated variables, MVs, we, or the operator, will have high and low limits. And those are the boundaries of the process. So the APC application, using the model, will try to, the first objective of the APC application is to keep everything within the specified limits, within that boundary. But additionally, APC software has a linear programming economic function that it's trying to optimize.
The optimizer.
Yes, and that's the next step that you will talk about. Yeah?
So as I said, the controller keeps it within the limits. So you can see here that the flow controller is reaching its high limits of this value here, and you can see it's hitting its high constraint. So the controller won't let it do that, won't go beyond that. Now the question is, why is the controller going there? Well, that's because of the optimizer. The optimizer sits on top of the controller and it's telling it where it should be in between these limits. And how you set that optimizer is through an economic cost, and those costs are defined here. So for this example, if I can find it, here you can see the cost. So what I'm saying, the wording's not very good here. So what you can see here is that I'm saying that the feed gives me a profit of 100, and so that's why it's trying to push the feed in, and that's why you can see here in the optimizer that the variable's gone to the high limit. What I could do, if I wanted to, is I could make it that I actually don't want to put the feed in. Like I want to try and make energy as something that is more important to me. So what I could do is make this one, the power consumption, more of a thing that I'm interested in. And so what you will see in the optimizer, we have to give it some time, I think, it will start to change. Now that's going to the high constraint. What we could do with this one is bring this back down by putting a negative value. And you can see it's starting to go down. So what I'm saying now to the controller, which obviously you wouldn't do this in a real plant, is I'm saying the feed is not that important to me, and I want to run the ball mill as hard as possible.
So in other words, by putting a negative value there, you are saying we are losing money by increasing the feed, which is not realistic, but it's just for the demo. And you can see that immediately the system is changing the target, the optimization target, and it's trying to push the system towards another set of constraints, towards another set of boundaries. But the actual high and low limits that you specified originally are exactly the same. And that's the beauty about this, because you are solving not only the control problem, but the optimization problem, all with the same tool, with two different economical functions that are running in the same software in parallel. And actually, if the system gets too complex to optimize, you can switch off the optimization function, but you can keep on running only in control mode. So, in terms of technology comparison, this is where the APC technology brings most of the advantage, because a normal PID control, or probably an expert system based in rules or if-then-else kind of programming, it will do the control part very similarly probably to what an APC solution can do, but they don't have the optimization component. So in this particular problem, what we are trying to do, for example, for the ball mill, is to actually try to maximize the throughput, but at the lowest possible power consumption. So we are trying to solve